Good morning, everyone. I'm Yangfu Li from East China Normal University in Shanghai, and I'm the first author of this work. Our group studies robust text recognition for complex writing systems. Today I'll introduce MSA², a multitask framework for open-set Chinese text recognition. The central idea is simple. We bring together linguistic structure and visual glyph information, just as humans do, so the model can reliably recognize unseen characters. With that goal in mind, let me first ground the discussion with a brief linguistic background. To set the stage, Chinese characters are composed from radicals and structures. Radicals are recurring components that often carry semantic or phonetic cues. Structures describe how these parts are spatially arranged, such as left-right, top-bottom, several surrounding forms, and overlaid patterns. Why does this matter for recognition? Because identity is determined not only by which parts are present, but also by where they sit and how they interact. In other words, a strong recognizer should exploit both axes, components, and layout. With this foundation, we can adopt a formalism that encodes these two aspects in a machine-friendly way. Building on those basics, IDS provides a symbolic recipe for a character. Structures, such as left, right, and top-bottom, combine radicals into well-formed shapes. We represent a character as a binary tree. Internal nodes store structure components. Leaves hold radicals. A depth-first traversal then prints a unique sequence, that is IDS, for each character. This gives us a compact open-set description. With a small collection of radicals and structures, we can describe nearly all Chinese characters and match predictions against a lexicon. However, as I'll show next, IDS alone is not sufficient to reach human-level reliability. Even when two characters share almost the same IDS, a single structural discrepancy can lead to a dramatically different appearance. Human readers notice the mismatch between the supposed structure and the visual glyph and decide they are different. A second, equally important point: not all structures contribute equally. Errors in primary structures, those near the root of the decomposition, like global left-right versus top-bottom, are far more damaging than errors in secondary structures deeper in the tree. Most existing methods treat all structural bits equally and typically assume a single-style prototype for glyphs. By contrast, humans are naturally style-adaptive. We can read printed, handwritten, and artistic forms with ease. Motivated by these observations, we seek a framework that fuses IDS and glyph cues, reweights structures by importance, and adapts to diverse styles. That leads us to MSA². Motivated by these insights, we propose MSA², a multitask framework for open-set Chinese text recognition. It fuses IDS and glyph cues, reweights structures via structure-aware component encoding, and adapts to diverse styles via style-adaptive glyph embedding. Concretely, an input image goes through a backbone and sequence model. Two lightweight decoders then predict a linguistic code and a glyph embedding. Each is matched against its own lexicon, one built from IDS, the other from multi-style glyphs. We fuse the two similarity maps and decode the sequence, with CTC or attention, to obtain the final text. Let me unpack the two representation branches, starting from the linguistic side. SAYS asks a simple question: if primary structures matter more, why not encode them with more capacity? We take the IDS binary tree and allocate a dynamic representation space across depths. Shallow, primary structures receive longer codes. Deeper, secondary structures receive shorter codes, often half at each level. This design gives greater decision weight to the structures humans rely on most, directly in the similarity search. Compared with static equal-length encodings, SAYS produces more informative and more compact linguistic codes. It reduces meaningless padding, avoids hard truncation, and captures what truly drives recognition. Structure alone cannot explain the wide variability in appearance, especially across fonts and handwriting. Sage addresses this by learning style-robust visual representations. For each character, we render multiple styles, printed, handwritten, and more, and compute a style center as a pseudo-prototype. A glyph encoder is then fine-tuned with contrastive learning so that same character glyphs from different styles cluster tightly, while different characters separate. The result is a discriminative, style-invariant embedding that complements SACE. Glyphs are particularly valuable for basic characters and symbols whose internal structure is limited. Now, how does this two-view design perform at the sentence level? On comprehensive benchmarks that include scene, web, document, and handwriting text, MSA Square achieves state-of-the-art closed-set results and notable gains in open-set protocols where many test characters are unseen during training. The consistent advantage over strong linguistic baselines and glyph-based methods highlights the core message. Fusing structure and appearance, while respecting their different roles, is essential for generalization. If we zoom into single-character recognition, the trend remains. On handwritten and syntax character datasets, MSA Square outperforms prior art in both open-set and closed-set regimes. The gains are most pronounced in low data settings. When training classes are limited, SACE provides strong structural priors, and SAGE supplies style robustness, keeping performance stable even as the number of unseen classes grows. To understand where improvements come from, we ablate the design. Removing either branch, linguistic or glyph, leads to a clear drop, confirming that both views are necessary. Replacing SACE's dynamic depth-aware coding with equal-length codes weakens accuracy, validating the emphasis on primary structures. Disabling SAGE's contrastive objective reduces style invariance and hurts open-set recognition. Together, these studies show that multitask learning, depth-aware structural coding, and multi-style contrastive training each make essential, complementary contributions. Let's look more closely at SACE's effect. By allocating longer codes to shallow structures, the model becomes stable against local perturbations. If the global layout is correct, small mistakes in lower-level parts are less catastrophic. For complex characters that require deeper decomposition, SACE reduces redundant padding and sharpens lexicon matching, particularly when the maximum decomposition depth is large. In short, SACE aligns the model's inductive bias with how humans prioritize global layout during reading. We see a parallel story on the glyph side. Before contrastive fine-tuning, glyphs from different styles of the same character are scattered in feature space. After SAGE, they cluster compactly, while interclass margins increase. This effect is strongest for non-standard forms, handwritten and artistic text, where appearance variance is high. SAGE thus acts as a style-invariant lens over the visual channel, complementing SACE's structure-invariant lens over the linguistic channel. Let me wrap up with the main messages. First, structure-aware coding reduces linguistic redundancy and gives proper weight to what matters most. Second, style-adaptive glyph learning generalizes across fonts and appearances. Third, fusing linguistics and glyphs is the key to reliable open-set recognition. Limitations remain. Our approach assumes available IDS and renderable glyphs, and we do not yet model relations among same-type structures across depths. We view these as promising directions for future work. To conclude, MSA Square brings the model closer to how humans read, attend to global structure, respect local parts, and stay robust to style. Thank you for your attention. I look forward to your questions.